I'm Lorenzo Pacchiardi, and today I'm going to talk about my new work, which is called Generalized Bayesian Likelihood-Free Inference using scoring rules and estimators. If you're interested to know more, please visit my poster at the first poster session on Tuesday, 29th of June. So I will start by giving some background, and basically by defining what do I mean by Generalized Bayesian Inference. So I believe most people are familiar with the definition of the standard Bayesian posterior. And the idea is that given an observation y, you want to get posterior distribution for the parameter of the model theta given this observation. And that is proportional to the prior times the likelihood. If you want, you can write this in a weird way by the prior times the exponential of the logarithm of the likelihood. And the reason why I do this is that this is easier to connect to the notion of generalized Bayesian posterior, which was introduced in this work from 2016. And the idea is that there you just replace the negative log likelihood with a loss function between y and theta. And this loss function can be any loss function, generic. It is generic in a sense. And here in this expression, you have to fix the scale between the loss and the prior pi with this scalar value w. So what is the advantage of using this generalized posterior? The advantage is that theta does not need to parameterize the probabilistic model p theta actually. And the drawback is that you need to tune this value w here. So now what do I mean by likelihood-free inference? So in likelihood-free inference, people are interested in the intractable likelihood model, p theta, let's say. And this is a model from which you can simulate data by drawing samples from it very easily, but contrary, you cannot evaluate the likelihood p of y given theta. And this means that the standard posterior is inaccessible. Likelihood-free inference approaches basically allow to sample from an approximation of the posterior, and they rely on drawing simulation from the model in order to circumvent the missing likelihood. So the idea of this work is to use a generalized Bayesian posterior for likelihood-free inference. In our setup, theta parameterizes a probabilistic model p theta. So we want to take a class of losses L which use p theta. So I do this by writing L as a function S of the probabilistic model p theta and of the observation y. And this class of functions which take let's say give a value to a probabilistic model and then observations are usually called scoring rules. And also remember that we can only draw samples from p theta, so we need to select scoring rules which admit easy estimators from samples. This means that I will need to draw samples from my model and then use them to estimate the value of the scoring rule between the model and the observation from these samples. Now, how do we perform Bayesian inference with scoring rules? So first of all, what are more in detail, what are scoring rules? Right, a scoring rule again is a function between a probabilistic model p theta and an observation y, and can be thought of as a penalty which you incur when stating a distribution p theta for an observation y. It's kind of a loss function if you want. Now you can define an expected scoring rule if you assume that the observation y comes from a distribution, let's say p naught here. So you define the expected scoring rule by taking the expectation over y coming from p naught of the scoring rule p theta given y. And you write this in this way by overloading notation in the secondary argument. So we use as convention that if the second argument of S is a distribution as well, we are taking the expectation over random variable sampled from that second argument. So there are some properties of S which are of interest. First of all, S can be said it's proper if the expected scoring rule between p theta and p naught is minimized whenever your model p theta is equal to the actual data generating distribution p naught. And we say that this scoring rule is strictly proper if and only if p theta equal to p naught is the unique minimum. So this means that if you minimize these strictly proper scoring rules, your model will recover the exact data generating process. Right, so now let's get back to the generalized posterior, and we want to write down the form for the scoring rule posterior. So as I mentioned before, we will replace this L with a scoring rule between p theta and y, and we also consider here multiple observations y1 up to yn, and square root posterior is defined as being proportional to the prior times this exponential term, where you get like W, which is the scalar weight, and sum of square roots over all observations which you have. So now I will have a look at some scoring rules which we'll use in this work, and specifically we will consider some strictly proper scoring rules. So first of all, the log score is the most used, probably because it recovers the standard posterior when you use it. So basically the log score between a distribution p theta and the observation y is just defined as the negative log likelihood at that value of the observation and the parameter theta. Next, I discuss now the two scoring rules which I use in practice for the likelihood-free inference setup, and those are the energy score and the kernel score. So both of those you can see here are defined as through some expectations over simulations from the model. So you have, for the energy score, you have the expectation of the Euclidean distance between x, which is a simulation from the model, and the observation y, minus the Euclidean distance between two independently sampled observations from the model. And for the kernel score, it's very similar, but you just need to replace the Euclidean distance with the kernel k, which needs to be a positive definite kernel. And all of these scoring rules in this page are strictly proper. Right, so now in the likelihood-free inference setup, you cannot compute the score exactly, of course, as first of all, you don't even have the likelihood, right? So, for instance, let's have a look at the energy score, which I've written before. You see here, as I mentioned before, we have two expectations, which you cannot compute exactly. So, luckily it's quite easy to build empirical estimators for this, right? Because you can just generate m samples from your model, and then you just replace the expectation here, which you cannot evaluate, with the empirical mean, and you get an estimator, which is actually unbiased. And for the kernel score, you can do a very similar trick. In general, we will run MCMC, and whenever we need to evaluate the scoring rule here, we replace it with this estimator, which uses samples from the model. So this leads to a pseudo-marginal MCMC, with a target, which I write here in this way, which depends on the number of simulations from the model m. In general, this target is not the same as the original scoring rule posterior, which uses the exact scoring rule between the distribution and the observation, but you can show that they are close if m is large enough, let's say about 100 samples or so. And also we have a theorem that says that if your scoring rule estimators converges in probability to the actual scoring rule between the distribution and the observation y, as the number of simulations goes infinity, then with some minor technical assumptions, you can show that actually the target of the pseudo-marginal MCMC converges to the actual scoring rule posterior. Right, so I just want to mention that the Bayesian Synthetic Likelihood method, which is widely used in likelihood-free inference, is an instance of our technique by using a proper but not strictly proper scoring rule. I now want to discuss some properties of the scoring rule estimator, which we were able to establish theoretically and to verify empirically. So first of all, we have an asymptotic normality result, which generalizes to the Bernstein-von Mises theorem for standard posterior. So here we assume the observations come from a distribution P0, let's say a data generating process, and we consider them as being random variables. So in this theorem, we need to assume that the minimizer theta star of the expected scoring rule is unique. Then with some technical conditions, we can say that if in P0 probability as the number of observations goes to infinity, then our scoring rule posterior converges to a normal distribution which is centered in the theta star, the minimizer of the expected scoring rule, and which has variance proportional to a matrix which generalizes the Fisher information matrix, and inversely proportional to the number of observations and the weight which you use in the definition of the scoring rule posterior. And we give a more rigorous statement in the paper if you're interested. And then the good point is that if your model is well specified and S is strictly proper, then theta star is guaranteed to be unique, so that this theorem holds. We also provide a result with a different flavor from the asymptotic one, which is called finite sample consistency. And this provides some finite sample guarantee on the posterior mass close to the minimizers, which can be unique in multiple, in this case, of the expected scoring rule theta star. This also works for misspecified models, and it guarantees that for n going to infinity, the posterior concentrates on the set of minimized theta stars. And this holds for the kernel score posterior and for the energy score posterior whenever the space of x, let's say of the observations, is bounded. This result is quite similar to what is found in these two previous papers, and we took inspiration from the second one to derive this proof for the theorem, which you can find in the paper, of course. We show this empirically in the paper with this G and K model. Here we report an experiment, but we have some more there. So here we have a model with 4 parameters, which are in the 4 columns, and we have 3 different methods, which you have the synthetic likelihood and the 2 scoring rules, which we use in our setup. The observation is generated by a parameter value, which is the vertical green line. And you can see here we have posteriors for an increasing number of observations, from 1, which corresponds to the green light here, and up to 100, which corresponds to the dark blue. And you can see that the energy and the kernel score posteriors concentrate approximately around the true parameter value, while the Bayesian synthetic likelihood does not. And the reason why it doesn't is that it doesn't use a strictly proper scoring rule. Right, so we also prove a form of outlier robustness, which is called globally biased robustness. And this means that if a posterior is globally biased robust, the worst possible infinitesimal perturbation in the observation leads to a finite change in the posterior for all values of theta. Of course, you can find the rigorous definition in the paper as well. And we prove a theorem in the paper which states that the scoring rule posteriors are globally biased robust for the kernel score, as well as for the energy score if the space is bounded again. And again, this is inspired by this previous work, and we have, of course, the rigorous statement in the paper. So we verify this empirically in a normal location model, which is a univariate normal distribution with known standard deviation and unknown mean theta here. And we consider 100 observations, the bulk of which is generated from this model with theta equal to 1, and we have some outliers. And epsilon and z here are 2 knobs which control the proportion and the location of outliers. So basically here in this graph we consider in the first row we fix the location of the outliers to 10 and we vary epsilon from 0 up to 20%. In the second row instead we fix the proportion of outliers to epsilon equal to 10% and we vary the location of outliers from 1 up to 10-20. And you can see that the standard base posterior is quite sensitive to the number and the location of outliers, while both posteriors, which we consider the kernel and the energy scoring rules ones, are instead quite insensitive to the number and location of outliers, and they concentrate around the true parameter value, which is this vertical dashed line. So finally, we also study the effect of this W in the scoring rule posterior. So if we get back to the scoring rule posterior, you see that this W here has an important role. So we investigate empirically how changing W impacts the posterior distribution for 2 different models. Here we consider the MG1 model, which is a queuing model with 3 parameters. So here in this plot I show the energy score posterior, and I show each row represents a different pair of posteriors of parameters, and each column represents a value of W from 11 up to 56. And you can see that actually the posterior becomes narrower and narrower as W increases. And this is quite expected from looking at the form of the posterior distribution. Finally, we also give a heuristic way to tune W in practical cases if you don't want to do this analysis. Right, to wrap up, we provided a new way to perform likelihood-free inference, which is based on generalized Bayesian inference using scoring rules. And differently from standard likelihood-free inference techniques, we do not approximate the standard Bayesian posterior, but rather we consider a generalized Bayesian formulation. And we show that this enjoys some useful properties, such as outlier robustness and consistency. And in practice, we use a consistent estimators of S from simulations from the model in a pseudo-marginal MCMC setting. Future directions for explorations are trying out some other scoring rules. And first of all, then we found that MCMC is probably not the best options for a large number of observations, as the posterior is very narrow and MCMC does not perform well. So we want to explore variational inference in this. And finally, we want to perform a more extensive study of model misspecification. Here are some references for if you're interested, and thank you very much.